All right, so a couple people have been asking me, and I've been noticing it in some work, that we're not really grasping Hooke's law. So let me show you another demonstration of that. We have a spring here, all right? We have a spring here, and we set it equal to basically, it's exactly at 1 meter above the ground. I'm gonna attach this mass to the spring, and we're gonna see how far the spring dips, and that will show us the stiffness of the spring. So give me 1 second to attach this mass. So as you can see, the mass causes the spring to expand or to stretch out. And there it is right there. Our mass is applying a force to the spring. The force that we call it is weight. Remember, it's the mass times gravity. So whatever this weighs, or whatever this mass is in grams, or kilograms really, we want to put this in kilograms, transfer this to kilograms, and then multiply it by 9.8. And that is the force of gravity, or the weight that's hanging on the end of this spring. This spring stretches out, and we see that it stretches all the way down to about 40, and really if we flip it like this is really how you should be looking at it, 40 centimeters. So if we transfer that into meters, we'd say, okay, 0.4. So give me 1 second. That mass we hung on the spring weighed 118 grams. So change that into newtons. We'd say, okay, 0.118 times 9.8. And we say, okay, that's equal to 1.16 newtons. All right, so that's how much force is on that spring right there. The weight of that. So Hooke's law says, okay, the force on a spring is equal to negative kx. Our x is how far the string stretched, or the spring stretched in meters. So let's plug in our numbers right here. 1.16 is equal to negative k times 40 centimeters, or 0.4 meters. Now we just divide over by 0.4. So let's divide this by 0.4. And we see, okay, the K of that spring is equal to 2.89 newtons per meter. That's Hooke's law. Right there. That's how you would solve Hooke's law. So hopefully this is helpful. If not, reach out and let me know.